Hello, and welcome to Science on Wednesday. We're talking about thermal expansion of solids and liquids, temperature scales Fahrenheit, Celsius, and Kelvin, and converting between them. We're also going to talk about absolute value and molecular motion. Let's get into it. Where we left off last class was talking about higher temperatures, things tend to expand. At lower temperatures, things tend to contract. Expand, take up more room. Contract, take up less room. And I told you about a rock concert versus a slow jam or smooth jazz concert. Let's talk about that in terms of those things. As a substance heats up, it expands. As a substance loses heat, it contracts. Okay, that's the takeaway. So, rock concert, all right, high heat, rock concert, people are dancing, they're moving, they're shaking, they have lots of energy, okay? What that means is they have to expand. They have to get farther apart so they don't hurt each other, okay? High heat, movement. So if you're at a low heat environment where you are like a slow jam or smooth jazz concert, people are going to get closer together, all right? They're going to contract and they're going to get closer particles together. So there it is. All right, let's move on. Okay, thermometers and thermostats. All right, a thermometer, like we've talked about, has liquid inside, and it typically measures temperature in fluids. That's most typically, okay? They do it by means of a tube filled with a liquid, either mercury or alcohol. The reason we use mercury or alcohol is because they have a very low freezing point. All right, it won't break the bulb. In this case, this is alcohol. As temperature increases, the volume changes, and we're going to talk about that now. All right, in the thermometer, as temperature increases, the liquid expands and takes up more space, and it increases volume. So a thermostat is a little different. A thermostat actually controls the heat in a system, all right? Measures and controls temperature, meaning it will turn on and turn off your system to add or remove heat from your home, a building, a car, things like that. It does that by means of a bimetal strip. Actually, your car is a little different. It's a little wax ball. But in this case, it's a bimetal strip. And I'll show you an example. Two metals are joined together. That's the bimetal. All right. In this case, it's a coil of wire or two wires sandwiched together with little rivets or glue or something like that. I have here an instance of a thermostat. This came off of a person's house, all right, that I ransacked. This is an older thermostat, older style. As this moves, this tells you the temperature of the room. If it gets up to a certain point, if it gets past this point, it will turn off the heat. How it does that is if you take off this front cover, which is all torqued up from my students pulling on it, this is a bimetal strip. This is a bimetal strip. This coil of wire has two metals sandwiched together. As they heat up, they expand, but the two metals expand at different rates. So it actually coils and uncoils that pointer, that smooth coil of wire, and it changes its shape. So it's different than a liquid. So why I say that is because as temperature increases, the metals expand, but at different levels or different amounts. This makes the strip bend or the coil rotate. And that's how a thermostat works. It will turn on and turn off your heat in your house. All right, let's move on. All right, let's talk about temperature scales. Temperature scales are what we've seen similarly on a thermometer, where we have Fahrenheit and we have Celsius. It tells us the temperature in both at the same time. All right, let's look at this in terms of why we have two systems and why we might have three. So, scale is Fahrenheit. The units are degrees Fahrenheit. Water boils at 212 and water freezes at 32. That's a fine system. All right, that's a system, all right, with this thermometer that we use in America. It's a fractional system, and we'll talk about why that's important. And the advantage is it's more precise. The reason I say it's more precise is because between 32 and 212, there are a lot more little lines there, all right, for whole numbers than there are between 0 and 100. Look at all the little tiny lines. So you can be at 71 and 72, two different Fahrenheit degrees, and only be at 1 degree in Celsius. So there's more accuracy with this scale. Why do people use Celsius? Mainly the world uses Celsius. All right, the world uses the Celsius, and its units are in degrees Celsius. Water boils at 100, it freezes at 0. The world uses it, and it's based on the metric system, and that's a base 10 system. 10 times 10 is 100, all right? That's an easy way to use it, and we'll talk about that. For now, know that the metric system and the Fahrenheit system and how we can go between those two. So, what do scientists use? Some scientists use this, but it wasn't as precise enough for what we needed. We needed precision. They came up with the Kelvin system. Kelvin, not Calvin. Kelvin as in a capital K, not degrees Kelvin, just kelvins. So water boils at 373 kelvins. Water freezes at 273 kelvins. And it does go down to 0. Well, let's talk about that 0 point, because that is a very perfect. Let's talk about that 0 point, because it is a point in which we need to talk about. This point right here is where there is absolutely no heat left in a system. All right, we can go below 0 in the Celsius range. We can go below 0 and things have not lost all of their heat. There's still heat in this alcohol if we are at negative 10 degrees. There is still heat, even if it's a solid. We're going to come back to this page. Let's see what I mean by that. You know that we have solid, liquid, and gas. The higher the kinetic energy, the higher you are on this scale. As you get lower the amount of kinetic energy, liquid has less kinetic energy than gas, and solid has the lowest amount of kinetic energy in those phases. Okay? What are the principles between these three? In a gas, particles are very far apart. All right, you can get space in between. They can bounce and move freely all throughout that shape. They have an indefinite shape. They can move within a shape, and they have an indefinite volume. They can change their volume. You can pressurize it and compress it. You can expand it and heat it up and make it take up more space. You can do that with a gas. A liquid's a little different. Particles are packed more closely together. They are free to flow. Not to move around in 3 dimensions, but to flow across. They have an indefinite shape. They can take the shape of its container, but a definite volume. You can't compress a liquid. And we'll talk about that later. Solid, all right, is particles that are arranged in regular repeating patterns. They're closely packed together. And they have a definite shape and a definite volume. Okay, that's important to know. A definite shape and a definite volume. You can cut that, but you can't allow it to flow past each other, the particles, and they can't freely bounce across each other. They are packed closely together. So why is that important? It's important because even a solid has molecular motion. Even those little dots, those particles in that solid are still moving. Not past each other, but they are moving. They're vibrating. They're shaking. They have energy. The molecules have energy, they vibrate. I just said that. Until temperature goes down far enough that an object has no energy, no heat. And that's the point called absolute zero. No energy and no heat, that's absolute zero. That's where all molecular motion stops. And that's the point on the Kelvin scale that is 0. 0 kelvins, absolute zero, 0 K. OK is what a lot of people say. Actually, I don't know if they say it. I say it. So 0 kelvins, absolute zero, no molecular motion. Let's go back to that thermostat. Okay, on here, that point 0 is the point a substance particles has no kinetic energy or no molecular motion. You cannot have negative kelvins because at 0, there is no heat. There are no joules of energy. So you cannot have less than none. Okay? This substance doesn't owe energy to somebody else. It's not a negative hypothesis. No. It has no energy. The last thing we're going to talk about is converting between Fahrenheit, Celsius, and Kelvin. All right? So, if you know Fahrenheit and you want to know Celsius, this is the formula you use. You plug in the Fahrenheit number, because that's what you know. You subtract 32, then you divide that answer by 1.8. Let's do an example. If you have a temperature of 98.6, the healthy temperature without coronavirus, and you need to know the Celsius, you plug 98.6 into the formula, you subtract 32, then you divide by 1.8. And there's your answer. 37 degrees Celsius is the normal body temperature. 98.6, same thing, equivalent. What if you know Celsius and you want to convert to Fahrenheit? Well, to do that, you would use the formula to solve for Fahrenheit. 1.8 times the Celsius temperature plus 32. Now these you're not going to memorize. We're going to write these in our notebooks and we're going to use these formulas to solve for that conversion. All right, so write down the formula. Don't worry about memorizing it. So, as an example, if it's 15 degrees Celsius outside, what is the temperature in Fahrenheit? 1.8 times 1.8 times 15 plus 32. 27 plus 32. You have to do that first. 59 degrees Fahrenheit is the equivalent to 15 degrees Celsius. Last, if you know Celsius and you want kelvins, Celsius plus 273 equals Kelvin. If it's negative 46 out, what is it in kelvins? Negative 46 plus 273. 227 kelvins is your temperature if it's negative 46 degrees Celsius. Gang, that's our class for today. Take these notes. We have a quiz due on Friday and a handout worksheet due on Friday as well. Take care. Let me know if you need help in office hours. I'll be available. Thanks.